So, and I can't do justice in 10 minutes, but I'm going to show 19 slides really quickly, so hold on to your seats if I can. I can do this first. This is the title. First of all, we had partial support for one student from ICTAS, and I greatly appreciate it. The people who have done the work have been Dr. Chin, who's now up at Georgia Pacific. So he moved from fuel cells to toilet paper, but you know, it's a very important consumable. So he's gone up there. Jason Rowland is a third-year PhD student, done most of the work. Ishan Maid is a second-year student. Andy Schaefer is a second-year student. See how I move this thing like this?
Just the right here.
Oh, okay. So this is the group. Andy's, I can't go through, take the time to go through who they are, I'm afraid, but I'm very appreciative. The old guy with the hat did nothing, so that's the usual situation. We have been working in fuel cells for about 10 years, and the critical monomer is shown there. It's a sulfonated derivative of a material made by solvent advanced polymers in Georgia. We developed a one-step synthesis for making this, and it's been widely useful in a whole range of different fuel cell applications as well as water purification applications. So there are two major areas of fuel cells we've been involved in. So-called higher power density is hydrogen air, has applications for vehicles and stationary power. And we've also been involved for several years now in what is called direct methanol fuel cells for portable power. And that's what I'm going to mention this morning, because that's the support for the student that has done that today. One of the critical issues is to develop alternate membranes to Nafion, sorry Bob, but this is to reduce the methanol permeability, which and increase the fuel concentration. So this is some size discrete chromatography on one of the copolymer family that we've developed. So it's this is a piece of equipment we got an NSF grant a year or so ago, and it does indicate for the first time what the molecular weights, molar masses of some of these materials are. They're in typically the 40 to 50,000 number range. They do develop a microphase separation, nanophase separation, I should say. This is some work on the left. It's Sachs' work cooperating with Bob Moore, George Moore. I think it was George Moore once. And we've just had a publication come out this year. Actually, it's out now. And on the right is a TEM, so it indicates that we can make these multi-phase systems, and they follow the rules that others have developed and we worked on earlier. This is the type of material we can use in cooperation with Don Baird. We can take 5 grams of material and make a meter of 20 micron film, so that allows people to evaluate these things in proper ways. My background is in polymer science, not electrochemistry. But I've worked with some good electrochemists, so I know not to be dangerous in that area, but I don't try to expel it. But we do a lot of mechanical testing, and these are ductile materials. These are materials that show a yield stress at around 50 megapascals and can easily show 30, 40, 50% elongation rate. This was an earlier result on membranes that have been transformed into membrane electrode assemblies. This, in fact, was not really part of this work, but I wanted to show it for some reason. This is cooperation with Los Alamos. We continue to have a great deal of cooperation there. I have former students down there and very active collaborations. These are thermally stable materials under nitrogen. In the salt form, they do not lose any weight, obviously, until about 400, 450 or so. So they can be fabricated in salt form. In the acid form, they're only stable to about 200 degrees, but that's way above the temperatures that we use. So I'm sorry that the ICTAS symbol is going over here, but this is the chemistry that's been well developed by others, and I agree with it, for the utilization of methanol as a fuel. Methanol is oxidized at the anode. What you want it to do is pass through the membrane as a protonated species, wind up reacting with a reduction product of oxygen at the cathode, producing water. One of the problems, and then the applications are indicated there, one of the problems is that Nafion and the materials of current state of the art have very high permeability through the film. And so instead of getting oxidized at the anode, they permeate through the film, go over to the cathode, get oxidized there, and set up a backwards current. This is referred to as the This is endothermic, so it subtracts approximately 23 volts from the 0.8, 0.9 volts you can get in the forward direction. So anything you can do to minimize that crossover is very important. And the obvious thing to do it is to make polymers that have lower permeability than methanol, which we've been able to do. In cooperation with Los Alamos, again, there's some numbers you can't see, but these are water absorptions of some of the block polymers that I've shown you. And these are ductile materials that they become a little softer, a little more extensible when they get wet. That's not too surprising because they are hydrophilic. They absorb sometimes 30, 40, 50% of the water, depending on how you make them. This is some data that on samples we made and sent to Los Alamos. And this is the typical performance curve, the voltage current curves. And the state-of-the-art concentration of alcohol is about 0.5 molar. That's very, very low. It's 1.6 grams per deciliter, roughly. So why is it so low? It's because the permeability is very high for Nafion. So one of the things we're trying to do is develop systems that can work at 1 molar, 2 molar, maybe 5 molar, maybe even 10 molar in some cases. So, but even at this 5 molar system, you can show that the performance is certainly equivalent, probably a little better than Nafion. The lower part of the curve here represents the so-called high-frequency resistance. That's the measure of the interface stability. And the lower numbers are better. How much time do I have? Negative?
You have several minutes.
Several minutes, okay.
No, you're fine.
All right. This is some recent work that we did during the last year, probably supported by past funds, on 2 molar systems. So we can go from 0.5 molar to 2 molar. And there we see a major advantage relative to the state of the art. And so the expected power density and fuel efficiency you can get from 2 molar is obviously a bit higher than it is from 0.5 molar. So we're following up on that some more too. I don't have time to go through some of the details, but there'll be a report, I'm sure, at some point that will have that. So another way that this is done is to calculate power density. And in the meantime, this, well, let's see if we can show, this is fairly significant. I can pull out my taking medicine now. I don't think I have to do any more of them. But I'm taking here. So this is some of the 2575. I won't go through the details. This is our material, and this is Nafion. So you can see this vector of 2, or maybe more than that in some occasions here. So the power density is higher, and that's positive. What we've done very recently is to try to make the hydrophobic phases even more hydrophobic. So instead of having some of the typical hydrocarbon systems, we've played some tricks, which I don't want to do that, from organic chemistry, and we've substituted the bisphenols, changed it from biphenol to systems that have alkylated system, maybe even as many as 4. And when you do that, this becomes quite a bit more hydrophobic. That means that the water absorption goes down. And this is a new method that Los Alamos has chosen to use. They've reduced the platinum quite a bit, which is also one of the other major issues. So this has, instead of 6 milligrams, it has 2 milligrams. So they can get pretty good results with 2 milligrams. And platinum is really the most expensive component in the system. Membrane is probably a distant second. So we can get significantly lower values here, but this is a first shot type effort. So again, the MEAs were made, and Dr. Kim, who spent 3 years with me here as a postdoc before he went there, he's now a senior staff member at Los Alamos, provided these measurements, and we have a very good relationship with him. He also got some pretty good power density. This is the first crack at it. It's a little better than Nafion at 0.5 volts. For some reason, it's not quite as good at higher voltages. So to try to keep to the time that's been given to me, I'll just a few conclusions. So we make controlled fluorine content hydrophobic oligomers. I didn't have time to go through how that's made, but we thought for a long time that in fact the partial fluorinated system was critical in order to provide a stable interface with the Nafion and the Nafion electrodes. And that may still be true in some cases. But Los Alamos has developed a new MEA procedure now that they think that may not be quite as critical. So in fact, I showed you the intrinsic viscosity viscosities and some of the mechanical properties. And this very recent result now, which we're working on for other reasons as well, will reduce the water absorption. I don't think I put that slide in, but it reduces the water absorption from about 40% to about 20%, which maybe is critical also in developing the appropriate interface between the Nafion lactose, and swelling is another major consideration. This one had a higher maximum power than the 212, for current densities up to